Welcome, and thank you for joining us for this webinar presentation. We are the Defense Systems Information Analysis Center, or DSIAC, one of 3 IAC domains in the DoD Information Analysis Centers operating under the Defense Technical Information Center, DTIC, within the Office of the Undersecretary of Defense for Research and Engineering. Our informative webinar series highlights current and emerging research and technology developments. It presents an opportunity for accelerating the DoD's leverage of these advancements by increasing awareness and fostering technical collaboration. DSIAC serves as one of the premier information research partners and curators of technology advancements and trends for the defense systems community. As such, our organization supports those working in the defense systems domain of DoD research and engineering. We do so by helping navigate the vast landscape of scientific and technical information, allowing our customers to get a head start on their technical projects. With an understanding of the defense system's DoD research and engineering landscape, we provide research and analysis services. We help unlock access to information, knowledge, and best practices from government, industry, and academia to stimulate innovation, foster collaboration, and eliminate redundancy. We hope you enjoy this webinar presentation and that it serves as a catalyst for community collaboration and improved DoD defense systems research.
All right, well, good morning, afternoon, evening to everybody joining in. Hopefully that video or little advertisement video came through okay. My name is Brian Benish with DSIAC, Defense Systems Information Analysis Center. Thanks for taking the time for this webinar. I apologize for any technical difficulties with registration, getting the links. I know that was an error there. We're working through kind of some changes to our internal system that are causing having some issues and some bugs, but we're working through that. So I appreciate you all being flexible and being able to find your way to get in. Couple quick pointers before, while Chris is pulling up his slides and before he presents. For those who are in the AnyMeeting platform, the first thing and most important thing I want to point your attention to is the questions portal, questions icon, should be at the top middle of your screen. At the end of this presentation, we're going to do a little Q&A portion. So at any time during the presentation, if you have a question, go ahead and click that button, enter your question, and add it to the queue, and then we'll work through those questions in the order that they were received. If you have any issues, technical issues with the presentation, first of all, rest assured we are recording this, so we'll make the recording available afterwards for you to rewatch if you'd like. And additionally, you can dial in if you have trouble with the platform. The phone number and dial-in instructions were just sent out a moment ago, and you can find the slides to download directly from our website. The link was just shared here in the AnyMeeting chat for it, but if you went to the DSIAC.org website, went to this webinar's webpage, there is a hyperlink to download the slides, and you can follow along from there. I think that covers the bases on the administrative pieces of the webinar, so I don't want to take too much time. Chris, I'll hand the mic over to you, so to speak, and then I'll jump in at the end. So Chris, floor is yours.
Okay, yeah, thank you, Brian, and yeah, thanks to DSIAC and the members and sponsors for having us today. Yeah, so what we're going to talk about today is X-ray computed tomography, and specifically as a reverse engineering tool. So I realize reverse engineering, capturing design information is probably a core capability that's very important to the mission of DSIAC and its government sponsors. And like I said, I know we probably have a very diverse crowd on the line as far as experience with CT, reverse engineering. So my goal today is to kind of hit at a high level of what is computed tomography and how do we use it as a reverse engineering tool to support various efforts. So like I said, we'll cover a few different examples there. So yeah, we'll kind of cover what is reverse engineering, jump into a little more of a high-level overview of X-ray computed tomography and what we call industrial X-ray computed tomography and what that means. We'll show you a few general applications of X-ray CT, how it's used throughout numerous different industries. And then we'll dive right in and discuss more in detail of how it's used in reverse engineering applications. And we'll call out a few specific examples, mainly dimensional inspection, using X-rays, as well as looking at electronics, printed circuit boards, and there's the many efforts that kind of span that application area as well. And then we'll end with kind of giving some, again, really high level in the time we have, how do we make the most effective use of CT? So what are some of the things that determine our end product? How can we make sure that we get the image quality, the resolution needed for a lot of these very specific applications? And then we'll point you in some resources, and we can even continue after this as well if there's further discussion as far as additional resources and things specific to certain problems that you or your customers may have. So in this context, when we talk about reverse engineering, what we're talking about is recovery of a part's design, its mode of operation, or even design intent. So that can span multiple different things. We can look at, capturing geometric features on a part, and that can be as simple as maybe making measurements, building a template, all the way down to, processing out actual CAD information. So extracting point clouds, STLs, and then even some higher end CAD models that we'll discuss. Another one is material properties, so looking at, material structure, if it's a composite material, again, circuit, traces in a circuit board, things like that, looking at the actual material structure, backing that information out. It could be just generally looking at a part's function, so more maybe along failure analysis where we're qualitatively looking at imagery, looking at how a part is fabricated, how it's built up, what's on the inside, and deducing its function out of it. So that's another way, again, that really helps out in failure analysis. You may not need a full CAD at the end. You may just need to help uncover some of that design intent qualitatively. And then that jumps more into the failure analysis side of typically, in the X-ray CT world, a lot of what we do is more on the failure analysis side. So one thing we'll talk about is X-ray is a non-destructive testing tool. So it gives us the ability to run these types of experiments non-destructively, view hidden and internal features without doing anything to the parts. That lends itself naturally to a very, very powerful failure analysis tool where we can capture data without destroying or doing anything to a part. And then the other thing we'll kind of hit on, especially when we talk about electronics, is uncovering vulnerability. So not only can we look at recovering parts, geometry, material properties, but again, if we put that all together, we can maybe deduce where some of these parts are vulnerable, and kind of help cover up some of that. So we'll give a couple examples in electronics as we go. And then the other thing I'll mention as far as reverse engineering in this context is it's not always a nefarious act. So we'll talk about reverse engineering is very important for a lot of critical steps throughout a part's design and life cycle. So it's not always just trying to copy a part. Like I said, there's probably more uses than that are more in a positive realm of where we're trying to improve a part's function or again improve its reliability and get rid of any vulnerabilities. So at the highest level, when we talk about X-ray computed tomography, it is a non-destructive imaging method, and it allows us to see and prod around a part's internal geometry and structure. So we're able to view hidden features, cross-section parts, all non-destructively, and again, it can be a very powerful tool in that aspect. So a lot of times when people think of X-ray CT, it generally is CAT scanning. So the first thing that comes to mind in the general population is just the medical CAT scan. Being able to look inside a patient's, diagnose different conditions, and it can do that because we're able to see and visualize all of the different materials and things that would be inside, as you can see in the medical CAT scan. But one thing I will note is that medical CAT scan is actually a very, very restricted area of CT. If you think about using X-rays on live patients, we have to be careful with the ultimate dosage, so that ultimately controls how much energy we're able to use. If you've had a CAT scan with an implant or something like that with metal, that never really goes well. And that's because of the limitation that, we can't put very, very high energy X-rays through living organisms very well. And then the other thing too, is we're always trying to do medical CAT scanning very, very quickly. So both of those kind of constrain, what we can do in medical CT as far as penetration through bigger materials and resolution. So when we talk about CT, we're talking about industrial and scientific imaging. So on this one, we kind of take the reins off on being capped on using a certain energy. We can also acquire data in a much longer period of time And what that enables us to do is scan larger, denser parts and get much, much better resolution and image quality. So that's when we talk about industrial versus medical CT. That's really what separates it, is the ability to have the freedom that we're not worried about hurting the parts. Even at the energies we're using, there's still no material degradation at that point with most materials. And so the systems themselves look a little bit different. So this is an image of what would more or less be a typical larger industrial CT system. So the first thing you'll notice is we don't have a spinning gantry. We're actually just rotating the part on its own stage, and by doing that, we're again enabled to acquire a much higher resolution and get much more precise data that way. So most systems will have an X-ray source, as you'll see on the right-hand side here. Some imaging detector to actually collect the X-rays, and then our sample will rotate in between those. And it's not untypical for industrial CT, scientific CT, to get down to the 1 micron level in resolution, and even down lower than that. And it's all dependent on your material size and the actual composition of your material. But typically, we're talking anywhere from maybe sub-micron, all the way up into the hundreds of microns for resolution, imaging resolution on these data sets. So with that, again, that enables us to actually capture manufactured parts. So an example here you're seeing of on the left, this is basically the CT process. We're just spinning a part, 360 degrees and capturing X-rays all the way around. And from that on the right, you'll see we're actually building a three-dimensional model. So it's that volumetric model that we construct that then we can interrogate, slice in, look qualitatively, and there's also a whole lot of quantitative measurements we can do on that data set. In the end, you'll see we can treat it very similar to how we treat a captured CAD geometry. So we can make measurements and extract a lot of data. And one of the examples you'll see here is porosity that's been highlighted in that part. So as I mentioned, when we use CT in this type of world, there's a couple main areas. Reverse engineering can be very, very important in quality control for qualifying parts. So, this was big in castings with a lot of manufactured parts prior, and this quality control area has really, really exploded with additive manufacturing. So with additive manufacturing, we have a CAD file of a part we intend to build. We build a part. There's always some deviation there. And CT is a great tool to be able to capture that surface data, go back, see how well the part built. In addition, I will say with additive, more unlike some of the traditional manufacturing methods, in additive manufacturing, a lot of what we're doing are building very, very complex geometries. So we're embedding a lot of internal cavities in there. We're doing things that we couldn't do with traditional manufacturing. So because of that, in additive parts, we see a lot of hidden features that we really can't access with a laser scanner or a touch probe. And CT can be a very, very powerful tool there when we're talking about looking at internal passages, very complex lattice structures. Again, because typically if you're using additive manufacturing, you're using it because we have a lot of complexity in our part and design. We can also do, I'll talk a little bit about modeling and simulation. So again, to go back to the additive example, we have a part, we have an intended CAD that we're building to, the part comes out different. One of the neat things with CT is we can capture that full as-built geometry, and we can actually run FEA and simulation on the as-built data to see how it differs from the model that we intended to build. And I'll show a quick example of that. Reverse engineering is very big, I know, in the DoD community with part obsolescence. So we have these platforms that have been out for decades now, through multiple waves of recessions and suppliers closing up and then just parts going obsolete. So I know one of the areas that we've worked with several in the DoD is in capturing data on a part, to reverse engineer design for a part that's no longer available, and generate technical data packages for things that we don't have that data for. And then finally, on the hardware assurance side, so design validation, making sure the part was built or constructed as intended, making sure there's no hidden flaws, hidden vulnerabilities that we should be aware of. And then another one that's probably come up maybe more in the last 5 or 10 years now is counterfeit mitigation. So using CT to look at a part, whether it's an electrical component or a manufactured part, and tell if it's authentic or not. So maybe look for things in the design, in the part structure, to be able to validate its authenticity. So the first example I'll show is part qualification. So industrial CT kind of a lot of it has its roots in aerospace. So qualification of aerospace components, aerospace parts has kind of been closely tied with the industrial CT application area for quite some time now. So one of the biggest ones, and it still goes on today, is qualification of Inconel turbine blades. So this is an example here looking at a small turbine blade. So these are made of a relatively high dense Inconel material, has a very high melting point, can operate in the highest pressure parts of the engine. But in a lot of cases, these materials are being pushed to their limit. So even on some of these, the more efficient engines now, we're pushing the Inconel material to its limit. So what we have to do is embed holes and geometries in blades to help cool them as the engine's going, to actually keep the material operating at its optimal point. So what that results in is a very, very complex internal geometry that really can't be inspected any other way. So on the left, you'll see the result of a CT scan. So we CT scan the blade, capture the full geometry, external and internal. And then from there, we can go validate things like making sure the wall thickness doesn't exceed a certain minimum wall thickness requirement. And then we can go in, you kind of see a cross section on the right there of some of the internal structure that's in these parts. So again, without X-ray, without CT, we'd really have no way to validate, if the part we constructed or was manufactured for us actually, meets all that requirements. And again, the nice thing with X-ray is we can do that all without having to test the part. So without having to put it in a high temperature, high pressure environment to test it, we can validate that geometrically. And I'd say there are a lot of blades being qualified in this method now, and that's probably gone on for the past few decades at least. So we talked about modeling and simulation as well. I brought that up. So especially in AM, in a lot of cases, access to the as-built, as-manufactured geometry is very, very useful for computational analysis. So as I mentioned, you typically run SCA on your parts design to make sure it's in tolerance. But with additive manufacturing specifically, we get into a lot of areas of looking at things that have very, very complex internal supports and lattices. Topology optimization is a whole other field where we're actually using finite element to generate our design, and that can be very tricky too, because small deviations in the actual geometry can affect the part's performance. And then also looking at internal defects. So you'll see here a quick example of a small bracket that's been topology optimized. So again, we used FEA to generate some design file, built the part. We know the built part doesn't match the end part perfectly, or the model doesn't match the built part perfectly. So again, we can capture that as-built geometry, go back and check our FEA analysis on it to make sure that we're still in range, or to see what any deviations may do to our intended performance of that part. And then the same can be said for defects in additive manufacturing is a whole other area where we build these parts, we have these unexpected, unplanned defects. We need to know where they are, again, how they're going to affect the performance of the part. So the general CT data workflow kind of runs through, as I mentioned, we scan the part in that system diagram you saw earlier. So the part will go on the turntable. We'll capture the X-ray data you'll see here. So in computed tomography, it's not uncommon to capture several thousand X-ray images as the part's rotating. And these are fairly high resolution images. So that can be anywhere on the order from 5 to 30, 40 gigabytes, even more, depending on the resolution detector you're using, what kind of imaging acquisition method you're going after. And then the real magic of CT happens in taking that X-ray data, which is all two-dimensional, and then building that three-dimensional model. So that process itself is called CT reconstruction. So that's all done on high-powered GPU-driven workstations. And then our end product is that volumetric file. So in this case, you see the engine block there. So we can do a lot of things with that volumetric file, you'll see. One of the most important things in the measurement domain is we can threshold it and actually fit a surface to it. And we'll show a quick example on the next slide from that. But once we have that volumetric file and that surface on it, then again, we can treat it essentially as a CAD model or a point cloud model and do all these very, very precise measurements on it. So as I mentioned with CT, we end up with a volumetric file. And you can think of that volumetric file basically as a three-dimensional picture. So we call them voxels or three-dimensional pixels. every voxel has information about the part, so it'll scale with brightness based on the part's relative density. So if we have metallic things in there, they're obviously going to come out with a higher voxel value versus composites, plastics, things with a lower density that are attenuated lower by the X-ray. They'll have a slightly different grayscale. And then so what we can actually do is we can actually use those transitions to build a surface. And this can be a very, very precise method as well. There's a lot of work and ways to calibrate data. So in a lot of sense, there are a lot of people using X-ray tomography as a metrology tool. So we can understand its uncertainty, we can understand its limitations, and again, kind of put it in the toolbox with all these other, surface capture, geometry capturing tools. And again, that makes it very powerful. And there's a lot of different software packages out there to do that. One example we had here was the Volumetric software that we use, which again takes this voxelized three-dimensional data and allows us to do all these complex measurements on it. And then once we have that surface data, as I mentioned, that can be extracted in the form of a point cloud, STL. And then there's even newer tools now where we can actually take that to more functional NURB surfaces, higher level CAD, as well as one of the more popular ones lately has been meshing for FEA. So all that can be done directly on the CT data set, which gives you a lot higher degree of accuracy, precision, and really reduces the amount of time that it used to take to convert to a point cloud, go to a mesh, and all these in-between steps. So one of the nice things now is there are software tools to be able to process pretty much any type of geometry, any type of CAD you need directly from the volume data. And some of the other examples as well, doing processing directly on the CT data, so we can compare other geometries, so we can compare the CAD directly to the CT scan set itself, find out if there's deviations, set tolerances. Then we can also do traditional GD&T. So like I said, as I mentioned before, we can do these kind of first article-like inspections on parts that are maybe a little too complex or have internal features that aren't really accessible by what you typically use a CMM touch probe or a laser scan for. So that's one area there. And again, another example of looking at a small cylinder head here. So taking the head, scanning it, thresholding the data, capturing the surface data, and then one example you see here as well is we can also quantify defects. So in castings and additive, if there are embedded porosity defects, we can actually go through, segment those, and really quantify them as well, so we can get statistics about their size, morphology, and things like that. So it becomes a really, really powerful tool in castings and additive manufacturing. So now we'll talk about the hardware assurance side. So we'll kind of jump from talking about making measurements on maybe more manufactured parts to going more to the electronic side. And this is another very big area as well. And one of the motivations behind it is, I put up here if you guys have read the Bloomberg article, The Big Hack. So, regardless of what went on there and what happened, one of the really kind of important things that came out of that, I guess, was that everything in there was quite plausible. So whether or not anything did happen or the extent to it, it was very, it could happen. And this is, a big area I know for the DoD in securing the supply chain, especially with electronics. So in this instance here, the kind of the gist of the article is having a large server board, a small, device or a small change was made to the board. How do we detect those? So especially in today's global supply market, where a lot of manufacturers are just searching for more vendors, there's a lot of supply chain issues. How do we effectively, qualify these types of parts? And we'll talk a little bit about the role CT can play in that whole area of being able to, qualify a part, making sure the part is built as intended, is going to function as intended, doesn't have any hidden features or anything that's been kind of snuck on there. So what we'll talk about is some of the challenges we have in CT and electronics, and I want to introduce a few kind of concepts of how we do the imaging itself. And that'll kind of relate to what we do on these circuit boards. So one of the things in X-ray imaging is we have this concept called geometric magnification. So we don't necessarily have a lens like a camera. So if you have a camera, you want to zoom in on something, we can optically, manipulate a lens and zoom in and get higher definition. Because X-ray is a transmission imaging method, meaning that we're transmitting from one side of a part through the part to an imaging device on another, we have to play by the rules of what we call geometric magnification. And it's basically just like projecting a shadow on the wall. That's the biggest analogy we use. So if we have a large part, we have an imaging detector. If we zoom all the way out and put the part all the way back by the imaging detector, you can see here we're capturing the entire image of the part. But remember, we are doing that, but then we have a finite number of pixels per feature on that part. So that would be a lower magnification. If we want to zoom in on the part, we basically have to bring the part closer to our X-ray source, and then we just project a larger image on our detector. And what this does is this allows us to get higher resolution on the part. So this can limit us, because one of the things you'll notice is that in order to obtain a slightly higher resolution, we have to focus on a smaller area. So we have this trade-off between field of view and resolution that we really have to abide by. So that's kind of at the core of X-ray imaging. And that, as you can kind of see, that can be a challenge with some of these large motherboards, server boards. If we do have a large 16-inch board and we want to get, very, very high micron level accuracy on it, you can see some of the trade-offs we have to make of maybe looking at a smaller area, maybe getting a bigger detector, higher resolution detector. So those are some of the trade-offs that we fight in CT. We'll talk a little bit more about that. And there are ways to overcome that and some tricks we can play to, again, maximize our resolution on a given part. Another thing that comes into effect, other than just the general magnification, is what we call focal spot size. So this is related to unsharpness. So one of the things we'll see is even if we magnify on a part, we still have to be concerned with, our X-ray source is not a perfect point source. If it was a perfect point source, all the X-rays were coming from a point that was, infinitesimally small, there'd be no concern. In reality, that's not really what happens. The X-rays come from a small point that has a finite shape to it and size. And, when we get down on the order, on the several micron resolution level, that becomes significant part of the equation of making sure that we get good resolution. Again, the shadow analogy we use on that is if you have an open window, put your hand up, typically your shadow will be blurry. You get that same effect of unsharpness, whereas if you have a candle or small pen light, flashlight, you're projecting a much sharper shadow. So it all has to do with the size of your source. And like I said, most of the time it's not a big deal, but when we start getting into those very, very high resolutions, it becomes a really important factor in the equation. So that's another tool that we use as well of making sure that if we're imaging, electronics, things that we want to get a very, very high resolution on, we really want to make sure that we're using an optimal X-ray source for it to, really be able to get the best information out of it. So where all this comes together, especially in the circuit board world, is doing trace level extraction. So that's probably one of the more common things that we do is, we can take a multi-layered circuit board, CT scan it, and then we can actually interrogate the data, non-destructively remove all the layers. So this is probably one of the more important things that we can do. And there's a lot of things you can do with these traces. So we can compare these against print files. So we can extract these traces as image files, threshold them, compare them right back to how the part was built. There are also other tools as well as we can go back and, in the end, a lot of people want to go back and generate a full net list and part bomb. And that's part of the process. It's not necessarily a full turnkey process at this point. There are, a lot of things like component identification that CT can certainly help with, but that's one of the holy grails of putting all these technologies together to have a turnkey solution. But CT really, really plays a very important part of being able to, again, just extract the trace geometries inside. So you can see here we have a small, I think this is from a wireless headphone board. But again, going down, separating out all the layers and being able to visualize and actually quantify the traces. So these images could be thresholded and put out into other software packages. The other thing you'll notice too is we can see even quality of how parts are bonded to it. So we can do some level of component identification in looking at how components are attached, where some of the pin locations go. We can also look at things like defects in solder if that's significant. So this kind of gives you a sense of a lot of what can be captured with CT and exported with a CT file. So one of the CT and X-ray have really been used as a pretty essential tool in both quality and failure analysis of electronics for a long time now. So there's actually a lot of CT systems, software packages geared specifically for looking at solder, looking at things of quality and failure in electronics. But when we go to actually CT scan some of these larger parts, so you see the example of the motherboard on the image here. Again, large samples if they require very high resolution, it can be challenging to get the correct aspect ratio. So we have to play some tricks, use some additional techniques to actually get the better magnification and resolution we need. Another challenge we have a lot of is in imaging parts with what we call mixed materials. So we have PC boards that already have maybe metals in them and the fiber board, but then we also have cases where we have very dense heat sinks, solder, these dense materials that can cause streaking and artifacts. And again, there's a lot of tools that we utilize to help minimize those as well that we could go into in more detail. The other one too is a lot of these boards are becoming very, very dense in features and layers. So obviously our ability to manufacture boards and technologies is getting better. So we're making much smaller features. We're stacking more layers inside a board. So you can see the example of a cross section of a multi-layered board. So one area that becomes very important, we'll see in the next slide, is in resolution. And then one of the last things I'll say on this slide is when we're looking at even a large board, we take a motherboard and we're looking at 5-10 micron resolution. Typically, the first thing we always notice is that board isn't flat. So when we're trying to slice through it, having the ability to what we call de-warp the board can become very, very important there. And that's again, as you're getting higher resolution data out of these parts, that's something that we really want to pay attention to. Is our ability to de-warp the board, get everything on a flat plane so we can export that trace layer image we want. So there's a lot of work and things ongoing there to further streamline that process. Yeah, and like I said, the biggest kind of takeaway from the last slide is resolution certainly matters. So you can see two examples here of slicing through a board, at a lower resolution versus a high resolution. Again, when we're trying to extract those trace level features, find those traces and vias, even some of the micro vias, resolution becomes very important. We don't want those, as you see in the two cross sections on the left at the top. If we don't have sufficient resolution for whatever reason, those layers are going to bleed together. We're not going to be able to dissolve those very easily or resolve them, tell those apart. Whereas on the bottom, if we find ways and do what we can to increase resolution on the scan, we can actually then go in and extract those layers and get much higher quality data that in the end requires less post-processing to actually go through and then generate the data that we want out of it. So as I mentioned, I'll kind of talk here. There are a lot of ways that we can increase resolution and image quality. So as I mentioned, the goal of this talk was to kind of give the high-level overview. Really, each one of these could almost be a different talk in itself. So there are many, many methods in CT that we utilize to further enhance the resolution and image quality. Things like what we can make the detector larger, so we can magnify the part greater. We can do subpixel interpolation, so we can actually, imaging detectors for X-ray do have a limit on pixel size, so we can't keep making them smaller and smaller, so we have to, again, do other things to try and boost the resolution. And so one of the things we do is to make the detector larger, whether it's building a bigger detector or moving the detector around and stitching images together. So that's one very, very common technique to increase resolution. Another one is actually moving the detector in subpixel motion. This has been done in microscopy for a long time now. Again, to be able to recover what we call super resolution images or interpolate these higher resolution images. And then we can look at other techniques like helical CT. There's offset. There's even limited angle CT, where if you think about a circuit board, we don't have to rotate the whole board. We can rotate it at limited angles and try and get greater magnification. And then there's also laminography tools, where we're completely flipping, kind of how we capture the data. And it's really optimized for getting very, very high resolution on larger circuit boards. But again, we're kind of confined to looking at maybe a smaller window. So there are ways to use laminography, capture very, very small sections of a board at high resolution and stitch those all together. But one of the things you'll notice, as you try these different techniques is you're typically going to pay for them in more imaging time or more data and more data. So obviously the higher resolution we make these data sets, the more processing data, computing power we're going to need to actually get through these data sets. So that's certainly one thing to keep in mind. So it's always really a trade-off of determining what the resolution you need is. So that's typically one of the first things we do when we encounter a circuit board where we want to generate some data from it. One of the first things we do is determine what resolution do we need. So we can go in, we might know what the layer thickness is. So if we know what the layer thickness is, we can go in and determine what our resolution has to be. We can also do quick test scans to kind of measure, what are some of these small features that we're going to need. Because again, if we're capturing at a higher resolution than what's required, it's not always a good thing. We're going to spend more time acquiring the data. We're going to wind up with a lot more data to process. So, which doesn't sound too bad, but then when you have, again, some of these larger boards, a motherboard, for example, at a high resolution could be a couple hundred gigabytes of data. So effectively parsing that and the time we spend processing that is very important. So again, we want to make sure that whatever resolution we're imaging at is matched to what the customer need is and what that application is. But it all starts with the imaging as well. So none of this stuff we do to increase resolution or to get more out of the data really does anything unless we focus on the actual image. We showed you that abiding by the rules of geometric magnification, focal spot size, and then how we actually set up the image. Because again, if we don't do that right, we really can't enhance too much further. So it's really, really important to have that good image quality up front. So as far as how you access X-ray CT, so I mean, I know over the past several years, it's certainly way more accessible than it's ever been. So if we were to give this talk even 5-10 years ago, I think a lot of people, I would be surprised if a majority of the audience at that time had utilized some service or some ability to access CT and CT data. I'd say now it's probably the opposite. I'm typically more surprised in a technical audience if there's a majority of the people that haven't. So it's very, very accessible. There are a lot of sources, especially within the DoD. Most DoD research labs, university centers, national labs all have some, if not multiple, kind of prongs of this CT capability inside. So that really, again, it's really more accessible than it ever has been. And then there also are commercial service labs as well. So Evonik is obviously one of those. We have a few commercial service labs. There's a group of others around the country. And again, it's really kind of taken off in the last 5 or 10 years of just making it more accessible to, maybe people that don't have the need to have a system. So as I mentioned, a lot of times these will be in some larger installations, but a lot of small businesses, a lot of, small consulting centers, engineering consulting firms, won't have a need enough to really justify the level of investment it may require to get a system. So we've really seen, again, that's kind of blown up over the past few years of seeing more people with that specific need. And then I'll touch on a couple additional resources. So, if you look up, there's a ATEC event, which is at Evonik next, actually later this month now, it's the 1st of September. So we'll be diving in depth a lot more into some of these technical topics, especially around CT and additive manufacturing and electronics, and kind of how we do that technically, how we build up a capability to be able to support many different applications. So I would certainly urge you to check that out if you have interest, or reach out if you want more information. Another area we're seeing a lot more now is the IEEE Pain Conference, if you're not familiar. So this will be later this fall, I think early winter. This will be in Huntsville. So I would certainly recommend looking at this if you're very, very interested in electronics vulnerability. So there will be, at least a few papers and presentations at that conference that focus on, CT for general different applications within, assurance, hardware assurance, and electronics. So I would urge you to check that one out as well. And then just for general CT, typically the American Society for Non-Destructive Testing has a couple events a year, different webinars, things like that, again, familiarize broad across all industries, so not really specific to one. But that's a lot of place where you can find some resources, and certainly don't hesitate to reach out through DSIAC or to ourselves if there are any questions, or you have interest in finding resources, whether they be different communities, different content sources, or even looking at standards. So I know that's a question that comes up a lot as well, is, what practices and standards are there for certain industry areas, and there are quite a few scattered about depending on your industry and application now, more than there was 10 years ago. So that's another thing that we've seen a lot of standardization of CT, whether it be for metrology, for casting, additive manufacturing. So there's multiple pushes throughout multiple industries to try and standardize these processes. So with that, I think we're right on time here. So we kind of reserved the last few minutes here for any questions. I see a couple in the chat here. So if you do have questions, you can throw those in the chat, and I guess I'll kind of start walking through the ones that have been asked here already.
Yeah, perfect. No, Chris, thanks for the presentation. Hopefully my audio is coming through here good. Definitely very thorough, very interesting. We did have some questions come through, so I'm going to go ahead and put them up. Actually, let me ask you, won't let me do that until you stop sharing. Can you turn off your sharing?
Oh, yeah, I can do that. Yep.
All right. There we go. All right, so yeah, as Chris said, I'm going to go ahead and read out these questions for those who are dialed in, that we can hear them. Chris can respond, and then we'll just kind of go through in the order they were received. If you do have any other questions in the meantime, just toss them in the chat. Very top middle of your screen should be a chat icon. You can click that, add a new question, and put it in queue. So without further ado, first question asks, how difficult is it to clean up and convert the Daikon files or volumetric CT to 3D CAD or FEA?
Yeah, that's a great question. So one of the crutches of anybody in CT is the phrase "it depends." So I'll try not to use that too much. But in these cases, so it can be difficult. It can be easy. It can be difficult to do this. And the biggest thing with this is the overall image quality. So to give a couple examples, if we have a part that's all one homogeneous material, it's not maybe a plastic or a light alloy that doesn't scatter, doesn't cause a lot of artifacts, then it's very easy. So, we do a lot of, plastic injection molded part, lighter alloy 3D printed parts, where it's a very, very fast, nearly click button method to go directly from the CT volume data to an actual surface. But what we'll see is one of the things is when we do have parts that maybe have multiple materials. So if we have metals embedded in or denser metals embedded around, then that's where that cleanup process comes in. And again, there are multiple tools to do that, but it really depends on the quality of the scan and what you're getting. Again, our best case scenario is lighter, maybe up to titanium, even some smaller steel samples. If they're all homogeneous and we have good resolution, then again, we mainly just click a few buttons. A lot of that gets cleaned up automatically. But if we do have a part that maybe we get up into the Inconel, refractory metals, things that scatter or cause noise, a lot of that has to be manually cleaned up. So again, as I said before, a lot of it goes back to the initial scan. So that's one of the things that we really focus on, and I focused on my whole career a lot, is making sure that we understand what the end application is before we start scanning parts, because we'll see a lot of people get into trouble where if you request CT scans of a part without telling them what you're doing with it, they may have been able to set that up a little better, image it a little differently to get you better data, especially to do the CAD and FEA. But again, assuming the part, we can scan it with minimal artifacts. A lot of that can be done automatically now. So getting to an STL point cloud is very, very fast. Even getting to doing NURB surfaces, you kind of just follow the same process you would with a laser scan at that point. So depending on the geometries you have, you could really go to a full-fledged CAD model pretty easily if it's a simple part that you can fit those shapes and geometries to. So hopefully that sheds some light on that question.
Yeah, very good. Thanks, Chris. Very good. Go to the next one. Okay, so earlier in the presentation, you referred to dewarping. This question jumped off that and said, when you say dewarp the board, are you shifting the board or your clip plane?
So in this one, we're basically just deforming our clipping plane. So the board as is, we're not, we can try to straighten it out. The problem is the warping that we're concerned about is usually on the order of tens of microns. So, building a fixture to try and hold to that level, you may be able to go down that path. There may be people that have gone down that path, but typically the warping we're concerned of is not very, very broad and heavy. Again, it's typically on the order of tens of microns when we're looking at these small sections. So one of the things we can do is we can actually warp our clipping plane. So it can be a manual process now. I'm sure I always think there's better automated ways to do that. That's one of the areas that we're looking at, is how to more intelligently clip or dewarp these boards. But yeah, we're basically just taking the clipping plane and kind of warping it to what the board looks like. Again, to where we get one image of a consistent from layer to layer. So typically it's not a terrible process to do. Like I said, there are a couple software packages out there to help with that. I will say one of the challenges is when we're going to the very, very high resolution. What we found on certain boards is that not all the layers are warped equally, so that can take a little bit more time to go layer by layer and actually dewarp all those layers separately. So there have been instances where we've had to do that as well.
Very good. All right, thanks, Chris. Next question is asking you could comment on what the state of the art is on in situ deformation measurements using CT. For example, solder ball under thermal stress in a package.
Yeah. So there are, there are a few manufacturers that actually make in situ stages specific to CT and microscopy. So there are scanners out there that actually have an in situ stage in there. A few of the limitations. One of the big one is on our cycle time. So obviously it does take some time to capture. We have to capture data from multiple angles. How quickly we do it, really depends on the resolution, the image quality we want to achieve. So, one of the challenges in doing in situ on CT is, you can't do a high rate. Anything high rate testing becomes very, very difficult to do in 3 dimensions in an industrial scanner. If you look in academia, there's a lot of research things done on the beam line. So you can go to a synchrotron beam line where you can get very, very high flux and capture data very fast. But even a lot of those will use multiple beams, multiple detectors to do high rate stuff. But again, having said that, there are areas in the lower rate. So again, there are a lot of rigs that go in CT scanners that do, composite and additive testing, additive materials testing. So we can actually sync those up with the scanner, to be able to scan at certain loads and do things like that. As far as the application of solder ball, there may be some work out there on that. I would think one challenge we would have with that is the resolution. So going back to the slides I showed you on geometric magnification, one of the things with load cells is they typically take up space. So getting a load cell and getting the whole fixture very, very close to our X-ray source where we need it for very high magnification, high resolution scans, that can be a little difficult. And again, the other one too is, could potentially be done on solder balls. You would just have to design the right fixture, I would think. So we'd have to have a fixture that's small and narrow enough that we can get it very, very close to the source to be able to do that. So that would be one of the challenges I would see there of doing maybe on a whole BGA. It'd be difficult because we'd be looking through other solder balls. We'd have to zoom out a little bit to get the area, but it's certainly things that in the realm of what is done with in situ measurements in CT, but I can certainly see a few ways that could potentially be done.
Good. Thanks, Chris. All right. A few more questions. Next one says, are X-ray videos a possibility right now? Is there a push for that need?
So as far as X-ray videos, I assume what is meant, you can clarify in the chat if it's not. I assume what you mean is like a real-time X-ray.
Yeah.
So a lot of the CT systems, a lot of the imaging detectors we use can run at, several frames a second. So we can capture in a typical CT scanner. We do this with failure analysis a lot. If it's like a switch or a relay or something, we've actually done videos of operation. So that can be done. Again, there's a limit. We can maybe get up into the 15, 30 frames a second, maybe a little bit higher. We're not really in the high speed. There's a whole other world of flash X-ray and X-ray cine radiography, which gets into the hundreds of frames per second and up. So that's kind of a whole other realm separate from the CT that we see as well. But as far as video, assuming you mean kind of lower frame rate, continuous events, those can be captured with most of the same imaging panels that we're using in CT.
Good. Okay. Next question. Have forging grain direction inspection been successful? And if so, what resolution?
So I'll say on CT, not a whole lot. So seeing microstructure on metals with CT is typically very difficult. There's a few cases where maybe you can get some information out. And one of the challenges is, we're imaging the material. So we're not seeing, especially at the grain boundaries, if there's no gap at the boundaries, we're just seeing a single material. So CT is typically not used, especially with metals, for microstructural evaluation. Now, having said that, we can see defects that are the result of grain misalignment. We see the effects of it, but measuring it directly can be a real challenge with CT. So typically with that, you're going down to an SEM or some type of diffraction technique, which would be outside of industrial CT.
Great. Next question. How do you determine the expected resolution that you can get for a particular part scan? And what information is needed to determine that?
That's a good question. Yeah. So typically with this is, I showed, again, I'll rely back on that graphic before of geometric magnification. So we know all the parameters of the CT system software we're going to use. So really the only variables, the biggest variables in there are, again, our source size. So how big is the point of our X-ray sources? Our imaging detector size and resolution, that becomes very important, as well as that geometric magnification, right? So part of that geometric magnification is how big is the part. Obviously, the smaller part, we can obtain more magnification. Larger, we're going to zoom out. So one of the biggest things that we typically ask from customers or from people requesting data is, again, what is the size of your part? And what are the materials? That'll also come into play as well. Those are probably the two biggest ones. And then from there, again, we can kind of say, here's the best possible. Here's if we push it using certain techniques, we can go a little further. But typically the material composition, is it a super dense metal or a light alloy or a plastic or a foam? And then generally, what is the part, or maybe not the part, but what is the region of interest size? So there's a lot of cases where we don't have to scan the whole part. If there's a smaller region of interest, maybe we can get higher magnification. So yeah, region of interest and general material are the two big ones.
Yeah. All right, next question thrown at you. It says, do you have any tools that automatically stitch together multiple scans of different parts of a PCB if it's not possible to get to, and that stitch together multiple parts of a PCB if it's not possible to get sufficient data quality from a single scan?
Yeah. So there's kind of two approaches to this. So one, the first one that we typically use is, just make the detector larger. So we talked about, shifting the detector, doing helical scan, where we're trying to capture as much data as possible in a single scan, because that's typically going to be our best quality. But yeah, as the asker here points out, is that's not always the case. So even if we stretch that as far as we can go, do helical, do subpixel, there's still a limit to what we can get. So a lot of times we may have to zoom in even more. So as far as stitching different data sets together, I mean, the tools we use, the volumetric analysis tools, do have some automated stitching in them. One of the challenges we see with PC boards is, if there are components or things that are causing artifacts and ghosting, that can really affect it. So I wouldn't say completely turnkey automatic. It can be difficult. There are cases where it may work out just fine. But a lot of times there's going to be some manual seeding or something of a stitching algorithm. So it certainly can be done, and it can be somewhat automated. It just, again, it'll depend on the actual image quality of the board. One of the really exciting things is, I didn't get too in depth in it, but laminography is a technique where we, instead of rotating the part in the middle of the system, we're kind of rotating the system around the part in a geometry that's more favorable to circuit boards. So one of the cool things about laminography is that can be automatically stitched together. So that's another area that we use as well. If we're doing very, very small scans with laminography, we can more easily stitch those together in an automated function. And CT can, again, cause some challenges if the scan quality or there's ghosting artifacts in there. Because again, a lot of these are very, very high density of layers. So we have to have enough features to be able to seed and actually register the two images together.
Gotcha. All right, thanks. We have a few more questions in just a few more minutes. So next one says, do CT equipment manufacturers provide traceable materials and voxel artifacts for baselining and trending ongoing equipment performance?
Yeah, that's a great question. Yeah, so I mentioned there's a lot of standards development, especially in measurements metrology. So there are a few different ways to validate the measurements in your CT scanner. The one method I know that we use and I've used in the past typically has been, you'll see these structures that have, multiple spheres. So really the best way to kind of validate a measurement is to use a sphere-to-sphere distance or multiples. So what you'll see a lot of CT manufacturers using is these, ruby or ceramic spheres that are, calibrated. They have a set, dimension, diameter. So you'll see them put multiple of these on a fixture, and then we can actually use CT to measure the, point-to-point distance between them. So that can be used to validate and correct for any CT misalignments. And so if you look there, one of the standards is the VDI 2630, I believe, and there's a US ISO working group that's kind of shadowing them. But they've actually put together, a more or less standard guide to how to calibrate CT scanners. So as I mentioned, I believe it's VDI, VDE 2630. So if you look that up, you'll see a set of documents that acts as kind of a guide of how to do that voxel qualification and calibration.
All right, very good. Well, one more minute, one more question. I want to honor the time here. So next question is about pixel push. It says you mentioned a technique, pixel push. How does that improve resolution?
Okay, yeah, so pixel push is our name for what we call sub-pixel interpolation. So basically what it does, if we have an imaging detector, we're essentially moving that imaging detector by half a pixel in each direction. So what we do is we capture data, at 4 different locations that are all a half pixel apart. And we can use super resolution dithering techniques to actually reconstruct a higher resolution image. So marketing will tell you it's essentially doubling the resolution of your imaging detector. In reality, there is a trade-off there, but typically we're seeing, anywhere from 60 to 70% higher resolution. So it's usually around 1.6, 1.7, to account for the artifacts of the dithering algorithm. But you can realize higher resolution images just by, again, shifting your detector. And the counter to that is always, well, why don't you make a smaller pixel detector? And that's very challenging in X-ray because we have scintillators, we have pixel sizes, so we can shrink that all, but then performance goes away very quickly. So there are a lot of cases where it's more advantageous to have a detector with a larger pixel, use a technique like this dithering to increase the resolution that way as well.
All right. That takes us to the top or bottom of the hour, I guess. I think we'll wrap it up here. Chris, thanks so much for the presentation and for fielding all these questions that were just spontaneously thrown at you. You did a great job. Hopefully everyone benefited from the presentation, the Q&A. And as you mentioned, if they do want to get a hold of you, they can reach out to us, you directly, for further information. But thanks again, Chris, for the time and the presentation.
Yeah, thank you guys, and thanks everyone for attending. Yeah, feel free to, like I said, reach out through DSIAC or to myself. Be happy to help you with anything you have.
All right, great. Everyone, have a great day.